And then we discussed that the key space itself is quite small, and there are some hardware that we can use those hardware in order to break the DES. Unfortunately, that is not the only way to attack it. There are some other attacks that were found about the DES, which is one of them is linear attack and the other one is differential attack. So in the linear attack, let's define what they are and discuss about them a little bit. So the goal of this attack is to find some sort of linear relationship between the key, message, and the ciphertext. For example, so let's say the goal is to find linear relationship among message, ciphertext, and key. For example, I can say if I, XOR the third bit of the message with the fourth bit of the message, and then I XOR that one with the C50, then I get like the fourth bit of the key. This is a relationship. Now maybe somebody would analyze, and it is linear. So linear, this operation over here, such as XOR, are linear, and or XOR those operations. So somehow somebody found, if they are able to find this relationship, that because of the way that the algorithm is designed, if you happen to combine these bits together, that would leak a bit of a key. And so the goal of this attack is to find all such relationship. So that means that if we find all this relationship, then we can use the MIs and CIs, the combination of them, pairs, to break the DES, right? So the way that we can break it again is that if we know many more of this sort of relations, then we can eventually use them to learn some of the bits from the key. And if we do so, maybe we don't find all of them so that we can completely break them, but we do find a lot of them. So the best known algorithm that we have found, we know that the brute force would take, the brute force attack that over here, what we have, or exhaustive search, would take 2 to the power 56 trials, right? It has shown that with the linear attack, we only need 2 to the power 43 because, with the help of this linear relationship between the message and the ciphertext, we are able to get some of the bits from the key, and then therefore we would fix those key bits, and then we would iterate over the other remaining bits. And that's why we only have to do a for loop over 2 to the power 43. Okay, so that was interesting. So if somebody can find this relationship, trust me, this is not easy. That's why we have, another kind of people called cryptanalysts that they study this in very deep, and they have their own techniques to find this relationship. Another sort of attack that we discussed was differential attack. So the idea of this attack is to study, so these attackers, they try to use this technique, this differential attack, to study that how changing the message would change the corresponding ciphertext. So imagine somebody is playing with this, some attacker is playing with this encryption system and send some message M, and then the key is fixed. Sending this message M, they get the ciphertext, and then they change one of the bits from this message, and they want to see how many bits or how far or how much the ciphertext would change. And again, they try to change another one, and again see the results. So seeing this would show, how well your algorithm is, utilizing this bits of message and the ciphertext to scramble the bits and then produce a quite random ciphertext. If you don't utilize the entire bits, sometimes it would happen that when you flip one of the bits of the message, the ciphertext doesn't change at all, for example, or maybe only one bit would change. But ideally, what we are looking for is that if you change one bit from the message, almost half of a bit from the ciphertext space should change. That is something that would really show that some algorithm is doing a pretty good job of permutation, so that it doesn't really show any, any relationship between, changing one bit and then you find some ciphertext from the distance, maybe 1 or 2 bits would change. So you will see that if you're doing that permutation, you will see that by close messages, the permutation would also stay close. So that can kind of help the attacker to break the algorithm. So let's just write it down. So the idea is that the study how changing M will change C, right? Change the ciphertext. So given that, so if it doesn't really change, if there is an algorithm that by flipping one or some of the bit of M, the ciphertext C doesn't change significantly, then that means that there is a non-linear relationship, right? That means that the goal is to find non-random behavior, right? So the best algorithm that they use this idea to break the DES, it needs 2 to the power 47 chosen plaintext to break the DES, right? As we said, we want to see how many changing M would result to we would want to study that. So how I start with one M, and then I would start to flick changes M and observe how C would change, the corresponding ciphertext would change. So the one of the best algorithm that is out there, it needs to do 2 to the power 47 plaintext. Send it to the algorithm, get the get the encryption, so that at the end it would be able to break the DES. Well, 2 to the power, it doesn't show that these guys are too far away from 2 to the power 56. But trust me, 56 bits for the key is already small. And if somebody can, cut it up to, 10% or 20% of the bits, that is a significant number. And that would save, that sort of, you could see that it is much better than running that exhaustive search for 2 to the power 56. So if this circuit can, break this algorithm with 50 in few hours, using these ideas, ideally, in theory, it should be able to break it faster. However, a lot of time, especially the differential attacks, are very theoretical and hard to implement, but we only use them to find a better upper bound for the security of the algorithms. So the differential attack, we know that DES should be 2 to the power 56 bits secure, but we know that in theory, even though maybe we cannot implement this algorithm, but it can be shown that we can break it with after this many trial. So that would define a better gap, for our upper bound of the security. So these are very important results. So I think we have already learned enough from the DES. We've discussed the way that it works. It is kind of based on some Festile structure. And, most of the block cipher algorithms that you see on the market, unfortunately, everybody has a different design. And sometimes you would just fail to understand why do they design it this way. Well, for example, who said that the DES should work this way? Like we always scramble only half of the message and then we leave the other half alone, and then next round we do the other one. Why not we just apply the function to both sides? And those are very good questions, but it is the way that this author designed this algorithm. They also show that it would resist a lot of attacks. So that's why it is there. So after we discussed this many attacks and possibilities, and we learned that the key space should be much larger, then in the year 2000, there has been a lot of discussions that we need to substitute this algorithm, because after the year 2000, people have started to get much powerful, processors. And then, we need to get the cryptographic research committee, they needed to give a response to this attack that was found on a DES. So the study back then is that, they call a conference, and an open forum for cryptographers to submit their proposal, the algorithm that they think is the best, to the committee. Almost 15 papers were sent. On the first round, 11 papers were selected, and then there has been many security conferences. They discuss about every paper, and at the end, an algorithm called Randall ciphertext was proposed by 2 Belgian scientists, and this algorithm became the finalist for this round. So in this algorithm, the message space and the ciphertext space are changed to, they have changed to 128 bits instead of 64 bit in the DES. This is a significant change. And then the key length could be any of 128 bits, 192, or 256 bits long. So this is a very good improvement comparing to the DES, where the message space was small, the corresponding cipher space, also the keys length was small. So with these changes on message space and the key length, if now somebody wants to attack this algorithm, the brute force would look like 128 bit, right? Or a for loop of 2 to 100, 256. So these are quite large. And therefore, obviously, even with today's computational power, attacking this algorithm would be something very challenging. So let's look at the AES algorithm by itself and see how it works. So the first thing first is that the AES, unlike the DES that you saw that we were pretty much working with bits, we were doing operation on bits. Now we are basically working on bytes. So it is a byte oriented. So 1 byte is basically 8 bits. Remember that. And or the other way that we would see this one word is basically 4 bytes or 32 bits. We are in the year 2000. We have 32-bit processors. It also really matches the construction of what we have there, the 32-bit processor. The registers are 32-bit, so the processor are able to do a lot of computation on the 32 bits at a time. So that is given. We would like to define some variables for the AES algorithm. We have the number of the block, which is number of the block lengths is defined as number of the bits divided by 32. So if you want to interested in n of b, shows, for example, if you have 128 bits, then we are talking about we have the block lengths of 4 words. So this is that we are going to use some variables that we use in the algorithm. And then the number of the key can be again 4 words, 6 words, or 8 words. If it is 8 words, we are talking about the AES with 256-bit key. And if it is, we are talking about the key, a number of the key block is 4. We are talking about the AES with the key length of 128 bits. And AES algorithm, just like the DES, it is also iterative encryption, which means that we have a for loop. Again, some rounds would continue to happen until we do all the computation, and then we produce the corresponding ciphertext. So it is as we said, the number of rounds is a function of number of blocks and also the number of the key. And for the case that, for example, you'd have a table. Actually, in this lecture, we are only looking into where the number of the block and number of keys forwards. So then we would have 10 rounds in total to do the encryption. So in the construction of the algorithm, the way that the algorithm works is that we receive a message, we would put the message into some variable called a state, and every round, depending on the round and the key, we would do different operations on this state, and then we would apply the changes onto the state. And then at the end of the round 10, the ciphertext would be whatever the value is in the state. So that would be our temporary variable. So the way that we would generate the state is as following. So suppose my M message space is 128 bits. Okay. So my M, when I choose a message M, as I said, we are working on bytes. So the smallest thing that I have is a byte. So I have M0, I have M1, all the way to M15, right? So I have 16 bytes. Every byte is 8-bit, and together I have 128 bits. So this is the message, the way that we would see it. When we construct a state, now we are talking about block cipher. You understand why we are talking about, name it block. So the way that we would start the algorithm, the first thing is to initialize the state variable. So this is our state variable. Okay, so we would start to put our message into the state as following, like this. It would be M0, M1, M2, and M3, right? So all together, and I will continue with M4, M5, M6, 7, all the way to M12. So I copy paste my entire message into this block, and as you can see, I put them in column by column, right? So this is what we call it a word, which is 4 bytes, right? So this is the definition, the way that the AES would receive the message, and then we would copy paste this message into the state. And there is a reason why we do that. We will feed it up in this way, and then you will see it very soon, because most of our operations are column oriented, and things would start to make sense when we get there. So let's go and see the algorithm by itself. So this is the pseudocode for the AES algorithm. So the algorithm would receive a plain text block and a key, and then it is expected to return the ciphertext. And as we said, at the end, the ciphertext would be whatever value it is already in the state variable, right? So the very first thing that we want to do is that after we initiate the state, of course, we need to run the key generation algorithm. So prior to this, I want to run the key generation algorithm. to generate 10 different. We have 10 rounds, right? As I said, for example. So I generate key 1, key 2, all the way to key 10. Why do I have 10? Because as we said, there is a relationship over here between the number of block and the number of key. And for our purpose, we assume that we are using 128 bits key size, and therefore, we would have 10 rounds over here. This for loop would have 10 rounds. So in the previous page, we saw the number 1. We saw how we would initialize the state. So I will go back again. So this is your input message, plain text, and then we would copy paste it in a column-oriented way to generate our state. So the step number 1 is done. We would discuss how the key is generated later. And then the next thing we want to do is what we have is different algorithms, right? So, but let me just say one more word before we continue. 128-bit was our initial key. So we need to convert this one to, to key 0, from key 0 all the way to, okay, it's okay. So, so maybe I should change this one a bit. Made a mistake over here. So key 0, key 1, and key 11. And then we would need to generate 128 bit, be expanded to 11 times bigger bits, right? So that is the key generation algorithm for the AES. So once we give our initial 128 bits, we generate 11 keys. I forgot the first initial key that we add to the algorithm. And this key is an extra key that we need to expand it using our original key. So then, depending on when we get to the add key, is basically just XORing the keys. So we would see that one very soon. Looking into the rounds, so number 4, 5, 6, 7. Every time I have to do different operations. So the first one is a substitution byte. The second round is shift row on the state. And then I do mixed columns, and then I add the key. So let's see very quickly how this thing works. So in the beginning, let's discuss about the substitution bytes. So in the sub bytes, I take this matrix. Suppose this is my state matrix, whatever it is, right? There is this, so I take any element from this table, I apply a sort of substitution table, and I'd replace the value with whatever value that I have in substitution box. So that is the idea in a very abstract and high level. How does the sub bytes would work? So I'm substituting this byte, whatever it is in this location, according to the substitution table. I replace that one with some other value, and I would just write it back there. So this matrix is a state, and this one showing the same state after applying the substitution bytes. The second operation, let me change my color, is shift rows. So the idea of the shift rows is to shift the rows by this, by this way. So I would like to name it as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right, so these are the 15 bytes. I remember I denote them like this. And after doing shift rows, this would be the corresponding table. Okay, so the first row, I don't do any shift. I just let it be as it is. So I just copy paste it. Okay, and then the second row, I will just one shift, right? So it is again rotational shift. So when I shift it to left for 1, so 5 byte number 5 would come here, 6, 7, and 4 would go to the back. And then this one I'll do 2 shifts, and then what I get is that I would get 10, 11, 8, and 9, right? And then the last one I do 3 shifts, and then what I'll get is for after I do 3 shifts, I get 15, 12, 13, and 14, right? So this is how the row shift would shift rows would work. This is the operation. Every time we call this function, it would just move the value, shift the values as we have defined over here. And then we have the third operation. I'm just showing them into maybe not much details. I just want you to have like a very good graphical, imagination of what is going on. We would go into the details very soon. So then the next operation is mix columns. So in the mixed columns, the story would become a little bit different. So I want to look into the columns. I don't care about the rows anymore. So I will call this one word number 0, word number 1, word number 2, word number 3, and then what I want to do is that I would apply some function, let's say f, that basically would do some arithmetic based on with the input of every word. So word 0, word 1, word 2, word 3, and then I would replace them with the output of that f function, which is word 0 prime, word 1 prime, word 2 prime, and word 3 prime, right? So that's how I will change those values. And you would see how do we do that, but you see that we were doing something relating to the bytes, and then now we change into the words. So I would want to do some of the algorithm would want to do some operations on the words. And then the last thing that we want to discuss is the add key function. So the add key is actually one of the most simplest operations that we have on the AES. Suppose this is the current state, okay? And then I take whatever value that is here, okay? And and then this is my state. This is my round key, I. And then what I do is that I take the corresponding elements from the set, and then I XOR them together and I write it back to the state, right? So this would be also my state. Okay. So this is the simplest operation. So we are given the round key I, and then all I have to do is to take this as current state. I apply the key XOR it with the corresponding bytes in the round key matrix, and then with that I will be able to produce the state itself. So that is one of the most simplest way that we will produce it. Okay. Any questions so far? Is this clear? In a very high level how the AES algorithm is working. All right. Look like no questions. So let's get into a little bit more details. So we would have, before I give you some details over here, I would like to mention that I understand that you won't completely understand the details that I'm going to mention over here. The reason is because after this chapter, we start to go through the basics of the number theory, and I would explain in very much more details how we construct these, groups, what is a field, and all those stuff. So don't worry about it. By the time that we would finish the number theory, and if you come back over here, then everything would start to make sense. But it is just a very small part of that lecture, so we would just keep it as it is for after this chapter. But I would like to bring some small examples for you guys to understand a little bit of these operations without going into too much details. But I would like to write some notes for you so that in future you come back, you don't have to go back to the other slide, so you can have most of the details over here. So remember, sometimes we talk about modular operation. For example, we talk about mod 5. So I can say that any number, a. Oops. All right. It looked like I got disconnected for a second. So when I'm talking about mod 5 algorithm, mod 5 group, so we are having a numbers that mostly we are talking about numbers in this group are 1, 2, 3, 4, right? And maybe 0, depending on if I want to talk about 1, 2, 3, 4, right? So which means that, most of the time, remember that every time that you take two numbers, for example, I take 3 and 4. So I said 3 plus 4 mod 5. I'm just giving you some small example. We don't have to go into details. So the result would be 7. Remainder to 5 would become 2, right? The remainder. So the remainder to that is just like, the integer 2, which you will find it in this set again. So any operation that you do, you will always remain on this set. So in normal sets of Z, all the set of all the values. Let me actually talk about real numbers. We're not talking about Z. So on the real numbers, in the set of real numbers, what you have is that sometimes we talk about multiplicative inverse, right? So if I give you some value A, you multiply it to some value B, then the result should become 1, right? When we are talking about this set of real values, so the only time that this happens is that when you multiply some number to 1 over A, you get 1, right? So this is like, for example, I give you 5, you say that divided by 1 over 5, you get 1, right? 1 is a identity element. It's very important. There is a magic happen when you are working in some group of modular n or modular p, whatever it is, and you get this result sometimes with different values, and we call them multiplicative inverses. So for example, on this set, if I multiply 2 times 3 mod 5, the result would be 1. Why? Because 2 times 3 is 6, mod 5 it become 1, right? Weird. So I was expected to multiply 2 multiplied to 1 over 2 to get 1, but you see that in modular operation, sometimes different things happen. And this is what we are going to define as multiplicative inverse. And so just keep that in mind. So let's go back to our definition. So we always have maybe seen this group of integers, and we have worked together on those, different groups or set of integers or set of, integers mod some prime number p or large n. But it is also possible to define this mod operation on polynomials. So that is the idea that we are going to use in AES, that it is known as Galois fields. The way that we define them is that we are saying that our variable is x. We are going to define some polynomials on variable x that the coefficients are in Z2. that the coefficients can be either 0 or 1, right? They are in, for example, mod 2, we can imagine. So this means that a polynomial with coefficients over Z2, and what is Z2? We can define it to be 0 and 1, right? The mod 2, only remainders are 0 and 1. For example, I can say x5 plus 0x4, which becomes 0, plus 1x3 plus 1, right? So this is a polynomial. The values are x, the variable as x, and then the coefficients can be only of z2, which is 0 and 1. So you can imagine that z2 is any integer a in natural numbers from natural numbers, so that a mod 2, right? The resulting, if you take any integer, you computed the remainder by 2 divided by 2, the remainder could always be 0 or 1, right? For example, if we say z3, define them over z3, then the coefficients can be 0, 1, and 2, right? And so on and so forth. So now we come over here. So in the, let me change my color. And how much time do we have? Okay, a little bit. So we have two different fields that you could see we define in AES. This one is going to use in substitution byte, in sub byte. Bytes algorithm. And this is the group that we are going to use in mixed columns. Right? So you have two different groups, two different definitions for two different operations that we have. Normally, when we define a group, when we want to have, this is like what we define over here is a group of infinite, polynomials. We can have any polynomial. The number would be huge. But normally, if you notice in cryptography, we are very interested in this mod operation, mod sum prime, mod sum n. So we are doing the same thing, except that we define after this f2x, which is all the polynomials with variable x over z2, and then we define a polynomial over here. So this would be, or you can imagine that mod p, mod 2, mod 5, this is mod a polynomial. And then we're gonna define this one as something called irreducible polynomial. Or you can imagine that this is like a prime value, right? So imagine when you have a prime value, it cannot be divided by any number or itself, itself or 1. So we have, when we define this polynomial over this set, then we are going to have it contains all polynomials over Z2 with degree less than equal to 7. What does that mean? So the degree of this polynomial p that we define is 8. How do we find the degree? Is the exponent of the highest x. So imagine that any polynomial that we choose, if we divide it by this polynomial, the remainder cannot be x8. It cannot have x8. It should be less than that. So it would be any polynomial that the degree is less than equal to 7. Okay. I understand that this is way too much information on the first place, but just try to bear with me. Soon things will start to make sense. So why do we do so? So let me give you an example. If, for example, I set a polynomial. For example, I define x3 plus x, and then I add this one to x3. Let me say x5, x3 plus 1, right? which would equal to x5 plus, well, 2x3 plus x plus 1, right? And then we said that we will compute mod x8 plus x4 plus x3 plus x plus 1, right? So we said that we are in Z2, so the coefficient, we always compute the mod 2, so then the result would become only x5 plus x plus 1. And this modular is not really necessary over here because the biggest degree over here is already less than x5, so the result would be just this value. And sometimes we also want to do multiplication. So if I multiply these two things together, x multiply 2, x5 plus x3 plus 1, again mod that thing, mod x8 plus x4 plus x3 plus x plus 1. So let's see, what do I get? So let's multiply them together. So the first one, I get x8 plus x6 plus x3, right? x3 multiplied to x5, x3 multiplied to x3, and then x3 multiplied to x. And then the second one, we would have plus x6 plus this one multiplied to this one, x4 plus x, right? So what did I get? So I have 2x6 over here, so they cancel each other. So at the end, I'll get x8 plus x 4, right? Plus x, right? This is what I get. Oh, I'm sorry, I have x3 plus x. Now, if I divide this thing by what I had here, x8 plus x4 plus x3 plus x plus 1, and then let's see, what do I get? So it's just one time, so I just add them up together, x8 plus x4 plus x3 plus x plus 1. So this two would cancel each other, this two would cancel, this two would cancel, this two would cancel, right? And then the remainder would be 1, right? So remember that I said when I multiply two numbers and then the remainder become 1, just like these two integers, 2 times 3 mod 5, it become 1. It means that 2 and 3 are the multiplicative inverse of each other. The same thing happened over here when I multiply these two values, multiply these two polynomials, so I get the remainder of 1, which means that x3 plus x and x5 plus x3 plus 1 are multiplicative inverses, right? Right? Just like, remember 5 times 1 over 5, I get 1. So the same thing applies. Of course, when we are doing this computation, modular this polynomial. Okay, so I said a lot of the story, but why are these things important? Why did I bring this up? Why are we going to do any sort of polynomial computation? So remember that we are talking about bytes. So we are talking the operation on AES are depending on the bytes. So I can represent a byte as a polynomial. For example, if my byte is 0, 1, 0, 1, and then 0, 0, 0, 0, and then this byte is basically 0, 0, 0, 1, 0, 1, 0, 1. So imagine that these bits are corresponding to each other, right? So I can represent one byte as a polynomial. So these polynomials can be represented as a byte. So this one is saying that this bit is 1, so the corresponding bit was 1. So we don't have x2, it is 0. We have x3, it is 1. We don't have x4, it is 0. We have x5, it is 1, and the rest of them are 0. So every byte that I have in this state, right? So for this substitution bytes. So every byte is represented as a polynomial. So that is why we are having this Galois fields, and we have this kind of notation of irreducible polynomials. When we are going to do operations substitution bytes on bytes. We are actually every byte is an encoding of a polynomial, and that's why we are doing these operations. Okay, I think it's a bit past by your break time. Let's have 10 minutes break, and then we come back to continue.